Hello and welcome back. I see you made it to part 2. That's great news. And let's take a moment to reflect and celebrate on what we've done so far. We have went through the background, right? The problem that we're trying to solve. We tried to evolve, optimize I/O programming, and we have even built a server in C. And I wanted to start from here and explain a little bit on the way we built the server. HTTP is actually an application layer protocol. So meaning on which level does this protocol run? There are a lot of protocols, right? Some protocols are on the transport layer, some protocols on the network layer, etc. And HTTP is on the application layer. That's why we're kind of programming it ourselves. And HTTP is built on top of TCP because it needs a reliable connection. So definitely not UDP, right? And so what we're doing inside the code here is basically TCP. So we're just writing TCP, and what we wrote kind of adheres to HTTP and the HTTP protocol, right? We're kind of returning the expected format, and that's why this is a valid HTTP server. So if this is your first time writing a server, I wanted to say congratulations for following along and getting to understand how such complex topics work. With that out of the way, we're ready to proceed with our part 2, multiplexing. So multiplexing is the answer to busy polling. So instead of you asking the kernel, is this ready? Is this ready? Is it ready again? A million times, you basically just give the kernel like the whole list and you say, just let me know when any of these file descriptors are ready. And the kernel does the job, and then your application basically stays asleep until something actually happens. And so it's going to be single-threaded, but you can kind of listen to many file descriptors at the same time. So let's see how this is done. So we start with select. From Berkeley in 1983, it actually became standard by POSIX as the original I/O multiplexer. Now it's a little bit quirky to use. The arguments are a little bit not straightforward, but we're going to explain through code, briefly walk over how it works. However, the most important thing that we have to understand about select is that it uses bitmaps. They're readable, writable, exceptional bitmaps. And the idea behind bitmaps is that every file descriptor that we want to sort of check or subscribe to is going to have 1 bit assigned. And so if I have 7 file descriptors, I'm going to need 7 bit masks. And each file descriptor is going to have either 0 or 1. 0, it means it's not ready. 1 means the data is ready and we can read it. So this is the idea of a bit mask. And let's talk about how it is done exactly in the code. So this is an event loop, and let's suppose this is part of our servers, where FDs could be, for instance, clients. So these are connections like file descriptors, and we want to listen to see if there is data that is coming from a client in our server. So the first thing we have to do is create a bitmap. I'm gonna go all the way here. This is our bitmap. And the first step is going to be initialization. The second step is going to be the actual select. This is where we're going to block until there is data that is available. And the third step is going to be the processing. All right, so how does this work? First, we have our read set, which we're going to initialize with zeros. Meaning we suppose at first, or we have to clear the bitmask. So there is nothing, no data ready. We initialize it with 0, all the bits in the mask. After which we have to iterate over all of our file descriptors, and we need to assign this file descriptor basically to the read set. And so what this will do is that it will kind of compute the slot of that file descriptor in the bit mask, because the bit mask actually has a fixed size of 1024. I believe there is a variable for that. It is fd, or a macro rather, set size, one word, but was on the edge. So it's a fixed size, and so we have to assign a file descriptor to like a slot in there, and the next step is calling the select with our read set. And what read set is going to do, it's going to let us know if any data is available by mutating the array basically. And so the next thing, once we're out of this blocking instruction, we have to iterate over the set and check which of these file descriptors are ready. And that's what fd is set. Basically, this instruction does is that we're going to iterate over all of our file descriptors, and we're going to check if they are ready by fd is set. In which case, we're going to have to perform the read operation as usual. So data is ready. Now we can read, and then we can process the data and move on. However, you may have noticed a couple of nuances here, a couple of issues. First thing is that all of this is in while true. So while true, we're going to clear the set, and we have to do this. We have to reinitialize it again because select mutates it. And that's a problem, that every time we're going to do a select, we have to reinitialize our set. The second problem is that we have a fixed size of 1024. And there is a third nuance, is that every time we're out of the blocking select, we have to iterate again over all of our file descriptors to see which one is ready. So there are three problems, and moving forward from here, the goal will be to improve things. So, to recap, select. What hurts about it is that there is a hard cap on how many file descriptors we can listen to for read events basically, or for events in general, and that it's O of n per system call, where n is basically the number of file descriptors. And there is, of course, copy in, copy out, and bitmaps rebuild each time. Now, this definitely worked well in the 1980s. Oops. But we're in, at the time of this recording at least, 2026. So things has become way faster. And yeah, I mean, network devices are way more common nowadays. So the next best thing was poll from System V, 1986. So poll is the next cleanup. It's the same idea as select, but instead of 3 bitmaps, you pass an array of poll kind of ft struct. And since we're passing an array now, we don't really have the 1024 limit. The event fields kind of say what you want. So it's cleaner, but there are still problems, which we're going to talk about again. So what poll does is that it cleans up the API. So instead of 3 opaque bitmaps, you now have an array of structs. And this is definitely cleaner. So this time around, we have an array that's kind of pre-allocated with NFTs, the number of our file descriptors, and then we're going to initialize. So it's, as always, initialize the actual system call and then the processing. So we need to initialize. So basically saying each field of the struct is the file descriptor and what kind of event are we interested in. In this case, for example, we're interested in readability. And then notice that we do this only once, right? And our infinite loop, so to speak, starts from here. And now we're actually in our poll, and we're going to block until one or more of our file descriptors are ready. And once it's ready, we have to iterate over the number of file descriptors, right? And basically, if we have received events, our events, and poll in, so in case, it's basically if it is the event that we want to check, right? Then we're ready to read the data and proceed. And so we eliminated some of the problems, but not everything. We still have to iterate over all of our FTs. So realistically, it scales better. So now instead of 1024, you can listen up to 50,000 idle, so have 50,000 kind of connections. But also it's every event, even if one client out of 50,000 sends actual data, you're going to kind of traverse all of these 50,000 to find which one of these had the actual event. And this brings us to epoll now for Linux version 2.5.44 from 2002. And the idea is that you register the file descriptor once, and the kernel keeps an internal interest list, right? The kernel stores it, and we don't have to sort of send it again, and it keeps track of it. And this is better because now it solved the problem of, instead of O of n, where n is our file descriptor, it's O of ready. And so when we're going to loop over the received events, we're only going to get the ready events. And that's great. So let's look at an example. We're starting this time our event loop with the server as our parameter. And what we're going to do is we're going to create our epoll event, right? So this is, first of all, we have to create our the kernel side interest set. And then we have our event, epoll event, which means we're interested in the input sort of event, right? We're interested in reading. And this is the file descriptor that we're interested in kind of subscribing to, so to speak. Now this EFD, it's a, so to speak, an identifier of the interest set that the kernel has. And of course, the kernel doesn't give us the entire data structure, at least for epoll. It gives us an ID. And what we can do is that using that ID, we can do epoll CTL, and which means we want to sort of modify this list. And in this case, we want to add an event for this file descriptor. And what it does is that it's going to kind of add this event into the interest set at the kernel side. So now it's no longer having one call with the whole array. You can kind of do it incrementally. So you have an interest set, and you can add. It's not really push pop, it's more add, remove elements. And this is a pretty neat implementation because look at this. Now we have a while true loop, and we're going to have an epoll wait. So this is blocking, right? But it's going to return n, where n is the number of ready events, right? And we're interested in two things. So first of all, we have to check if the file descriptor of the ready event, if it is our server, right, it means we have received a new connection. So what we're going to do is that we're going to accept that connection from the server. And now that we have accepted that connection, we have a client basically, and we want to subscribe to client events in case the client sent us data. And to do that, we're going to do exactly the same thing as we did here. We're going to create a new epoll event data structure. And in this time, we're interested in epoll in and epoll et. It basically notifies you not just on input events, but when the state of the file descriptor changes, basically. Like if it becomes readable or something. And then using epoll control again, we're going to add that into our interest set, right? And with this, whenever new client comes, it's going to be pushed into the kind of because it's kind of a black red tree, and so it's going to be added in there. And if the event file descriptor is not our server, then it is definitely going to be a client, right? Because that's the only thing that we're pushing. If it's not a server, it's a client, and then we can just read the data, we can process it, and we can send to the client other data. And this is way more elegant. And yeah, we basically are receiving server and clients in the same epoll instruction. So with epoll, there are actually two modes. There is level triggered, which is the default, means the kernel tells you like this FD is readable on every wake until you actually drain it. Or edge triggered, it tells you that something changed. It went from not ready to ready, for example. And edge is usually faster because you have fewer wake ups, but yeah, it puts the contract on you kind of, where you must read from the buffer until you get the same E again error number, if you remember that. Otherwise, you miss your data and problems might occur. So usually beginners kind of stick to level triggered, but it doesn't matter too much. It really matters if you're building some high performance servers. So it does matter to some extent because epoll is still used. I believe that Node.js is still using epoll to this day. And that's because it has to be compatible with slightly older hardware. Yeah, because IOUing, which we're going to talk about later, is more or less, it's more modern, so it's not compatible with older Linux versions, so to speak. Next on our list is kqueue, introduced in FreeBSD version 1.4 in 2000. And actually, this is what is used on macOS to this day, if I recall correctly. I believe the reason for that is that macOS used to have a BSD kernel underneath. I could be wrong. But nevertheless, this is how we do IO programming in macOS. So it has more or less the same concepts as epoll. It actually predates epoll by 2 years. But the cleaner thing about kqueue is that it is one system call, which is kEvent, that is used to register new interests and also wait for events. And also it has a slightly higher scope in the sense that it supports signals, timers, file changes, process exits. So it's not just sockets. And yeah, it's the default standard on macOS. So let's look at the code. Same as epoll, we have more or less one initialization phase, right? And then we have kind of an infinite loop. Again, our epoll loop has the same server file descriptor. And so what we want to do is basically initialize our queue, right? And then we're going to create a kind of a change event here. And we're going to use that to register for our server file descriptor so that we can listen for updates, right? And then we emit that kEvent with the change parameter. And then while true, we're going to wait. And this time it is blocking. In the previous kEvent call, this is not blocking. It's not going to wait. But in the second one, it is going to wait. And because we have no kind of change parameter, and we're going to wake up with n events, and it's same as epoll, more or less. We're going to iterate over that number, and we're going to check if the file descriptor of the event, if it is our server, then we have a new client coming in. We're going to accept the connection, we're going to create a new event, right? We're going to register, kind of map the client file descriptor to that event, and then we're going to emit it so that we can subscribe to it. Otherwise, if we have an event that doesn't come from our server file descriptor, it is a client and we can read its data and process its data. Now, I actually want to make a small correction because what determines if k event is going to block or not, remember we can use k event to register event and then to wait for event. What determines it, if it's blocking or not behavior, is actually this parameter, which corresponds to max events. So this is basically the maximum number of events that it should wait for. So if anything below this number fires, then kqueue may fire, but you will not get more than 64 events in this case. And so if the number of events is going to be 0, then you're not, it's not going to wait because there is no number of events, basically. The next thing I want to talk about is the reactor pattern. So the reactor pattern is a design that most servers use these days on top of epoll and kqueue. You can already see the pattern in the C code where we have an infinite loop. If we have an event, then we process that event. Otherwise, we're looping, except in Node.js, for example, which is using libuv, it is basically just an event loop that tells you if there is something async operation going on or not. So if there is an incoming operation, you can switch to handle that function. Otherwise, you can do your own processing. It's called reactor pattern because it's reacting kind of to the outside world, but in reality, it's more of an event loop in the sense that to react, you kind of need to know that there is an event. So yeah, there is always a while, and there is a, epoll or k event, etc., etc. And that's it for today's video. In the next video, we're going to talk about a new, more modern models. I know this has been a lot of, it has been a bit more intense than the last video. I can't say it's going to get any easier, but congratulations for making it this far. Yeah, I really hope this has been informative. If you noticed any inconsistency, right, any issue, anything is unclear, if I got anything wrong, of course, feel free to let me know. And yeah, thank you for watching. See you on the next one. Have a good one.